Okay, so we will start today where we left off. Are you able to see the screen? Guys?
Yes, sir.
Yes, sir. Yes, sir.
Okay. So we
Yes.
said something about the common collector amplifier. We derived the equation. First of all, we uh, saw the H parameter equivalent circuit that is right there in front of you. Then we derived the equation for input impedance. Just to revise, just to recollect, input impedance for the device is equal to HIC plus HFC into RE parallel RL. Input impedance of the circuit is ZI, which is equal to R1 parallel R2 parallel ZB, where ZB is the device input impedance. Today we will start with the output impedance and gradually go on to the voltage gain and the current gain. Okay. So in case of the output impedance in this particular common collector circuit, you see that any variation in the output has output voltage has a significant effect on the input. Why is that so? Why this statement is there? How can we justify this statement? Because if you remember HRC, this is the HRC. What is the value of HRC? Yes, correct. You're right. HRC, because HRC is equal to 1. So the entire output voltage appears at the input to this particular device. Okay. Now to determine the output impedance, the signal voltage we will assume to be 0. So this part we will make equate to 0. So as if there is no signal voltage here, in that case I can replace it with a short circuit like this. Okay. And we will say that IB, now who is going to produce IB? IB is going to be produced because of this VO. Are you able to understand this?
Yes, sir.
Because we will assume that signal voltage is equal to 0, but still IB is produced. Why is it produced? Because you already have the output voltage affecting or other affecting the input. Okay, the entire output voltage is available over here at the input side, and that is the reason why I'll be able to have IB. Now this is only for the derivation purpose. Remember that without signal voltage I will never have the output voltage, but for derivation purpose we have to make sure that one of the sources is made 0. Okay, so the device input impedance, now what is the device input impedance here? That is ZB, which we have already derived. What is the device output impedance? Device output impedance. Look at the figure. ZE. So ZE, if I want to find out the impedance, what should I do? I should have the current, the ratio of voltage to current. That is the output voltage to the output current of the device. Output voltage and the current, output current of the device, that is IE. That is how I will be able to find out ZE. You're getting it?
Yes, ma'am. Yes, sir.
Now IE
Yes, sir.
is equal to what? HFC into IB. We already know this. Okay. When BS is equal to 0, which we have assumed, IB is generated by VO itself. We already have seen this now to begin with. So I can write IB as VO divided by what? It's a current. So we have to have a ratio of some voltage to what?
Resistor.
Ohm's law, some resistance. So what is the resistance on the input side? Total resistance on the input side, you can see here. It is this HIC. This HIC plus a parallel combination of R1, R2 and RS. You're getting this?
Yes, sir.
Sir.
So basically what I'll just reduce it this way. This is RS, this is R1, this is R2, all this in series with HIC, and here you have the entire VO
Yes,
because HRC
sir.
is equal to 1. Okay, something like this. So in the denominator, I'll have this as HIC plus R1 parallel R2 parallel RS. This is my HIV. Agreed? Do you agree to this?
Yes, sir.
Yes, sir.
Yes, sir.
So I can
Yes.
write from this equation, I can write IE is equal to HFCVO divided by HIC plus R1 parallel R2 parallel RS. Okay.
Yes, sir.
So I'm in a position to have IE now. And we already know, we have said that ZE. Now I can find out ZE. How do I find out ZE? We already have this equation here. It is simply the ratio of output voltage to output current, that is emitter current. This is device output impedance. So this is equal to VO divided by IE. So if I take a ratio over here, VO divided by HFC into VO divided by HIC plus R1 parallel R2 parallel RS. This can be simplified as simply, yes,
HIC plus
yes,
R1
HIC plus R1 parallel R2 parallel RS divided
upon
by
HFC.
HFC. So
HF.
what I get is the output impedance. So now I have obtained the output impedance of the device. Now look at what is the circuit output impedance. This will be easy. What is the circuit output impedance? That is ZO. It will be this ZE parallel RE.
RE.
RE. Yes, sir.
So now things are easy for us. So the circuit output impedance ZO happens to be RE parallel ZE. This is what we get. So what we have obtained is the output impedance equation for output impedance of the common collector amplifier. Generally speaking, this ZE, you can see, okay, we'll talk about it later. First, we'll complete the voltage gain. So next is the voltage gain. Okay. So voltage gain AV is given as the output voltage by input voltage. Now we have what is the value for output voltage? PO. How is the output voltage generated? See here. This current IE flows into a parallel combination of RE and RL.
RE
And
and
simple
RL.
Ohm's law, isn't it?
Yes, sir.
Yes, sir.
So I can write VO, which is generated as IE into RE parallel RL. This we can write as HFC into IB RE parallel RL. But now we have to find out what is IB. So what is IB? Remember, for this derivation now, we are not assuming our Vs to be 0. So this we have to again make sure it is not equal to 0. Okay. Whatever is the voltage appearing here, Vi, this is Vi here, and this is Vo here. Okay. So what is IB? It is as if I am having this voltage source. Let us okay, let's not get confused with this. Okay, we have to. This is Vi, which is parallel. I mean, which is in parallel with the R1, R2, and all those things. Okay, look at this Vi. We are talking about Vi and not Vs. This Vi. Okay, so as if you are having this, we are having as HIC, and here you are having another voltage source VO, and this is how the base current flows. So how can I write this equation? Can I write it as Vi minus Vo divided by HIC? Can I write it like this?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Okay. So I can write Vo as HFC into RE parallel RL. Now IB I'm going to substitute from this equation as Vi minus Vo divided by HIC. All right. Now on both the sides of this equation, I have Vo and I have Vi. And now I can find out the ratio of Vo and Vi and finally get the gain. So taking Vo common, bringing VO term, VO related terms on the left hand side, and then taking out VO common, I get 1 plus HFC RE parallel RL divided by HIC. I'm just expanding this bracket I'm expanding, and then transposing it on the left hand side. On the right hand side, what do I have is HFC into RE parallel RL into VI divided by HIC. Now I'll be in the position to have the ratio, the desired ratio, which is AV, which is VO by VI, and that happens to be HFC into RE parallel RL. HIC term will go away, taking this entire bracket on the right hand side again, the denominator. 1 plus HFC HFC into RE parallel RL. Okay, if you don't want to get confused, let us have this term here. Okay. This divided by HIC.
सर डिनोमिनेटर में आपने दो बार लिखा है 1 प्लस.
Oh.
Yes, sir.
Okay. Just let me do away with this. Okay.
Yes.
All right now.
Yes.
So what do you see here? HIC तो cancel हो जाएगा बॉस, लेकिन HFC into RE parallel RL. This is one term. 1 plus. So this term you can see here directly. Let us put it this way so that it is easier for you to understand. So call this term as this numerator as A. Okay. So what do we have? Simply like A plus divided by 1 plus A. You're getting this?
Yes, sir.
Yes, sir.
So what is apparent from here? Generally A is much larger than 1. Okay. So this nearly is equal to what?
1.
Yes. But always slightly less than 1.
Yes, sir. Excuse me, sir.
Yes.
Sir, while finding IB, we are using KVL in the loop.
Yes. This one. Here, no?
Yes, sir. The law
Yes.
used is KVL. Okay,
Correct.
sir.
Correct. ठीक है?
Yes, sir.
It is simply the current flowing because of the two sources. So what can we say about the voltage gain of common collector amplifier?
Approximately equal to 1,
But less than 1.
but less than 1 always.
Yes? Then why call it as amplifier? If you are having, so this is not a voltage amplifier. Please remember one thing, common collector does not give voltage amplification. Important, very important concept. Write it here. Common collector amplifier does not give voltage gain.
So सर अगर वोल्टेज गेन नहीं करेगा, नहीं देगा, तो सर फिर भी क्या वो एम्पलीफायर होगा?
Exactly, that is my question. Why call it as amplifier? And the answer will
So
be
current to
yes.
amplify.
Yes. We will see the answer in the next part. That is the current gain. Here we have HFC, which is equal to IE over IB. Again, like common emitter, using current divider equation, we can find out the overall current gain as, now I'll leave it to you for, because it is exactly the same as that of the common emitter. This happens to be RB RE divided by RB plus ZB RE plus RL. This is using where RB is R1 parallel R2. This derivation is exactly like common emitter. And here itself you will see that this circuit gives you current gain. So this is the circuit current gain. This is the device current gain. So the circuit current gain is larger in this case. So technically speaking, common collector amplifier is a current amplifier. Remember that. Okay. And many times we require current amplification. So such a type of circuit is normally used for current amplification. Okay, we will see more about this later on. The last thing that we will do is the power gain. So power gain is nothing but, so this is the transistor power gain, which is AV into HFC, voltage into current gains. Okay, whereas but AV is nearly equal to 1. So therefore, the device power gain happens to be only HFC. But circuit power gain is AP, which is AV into AI, and we already have seen that AV is equal to 1. So this is necessarily equal to AI. So the power gain that you get is equal to the current gain in this
Current
case.
gain.
Okay. Now the characteristics of this common collector amplifier, I just put it down here, are that it has very high input impedance, very low output impedance. If you remember the loading effect, okay, what was the requirement that there should be no loading or minimum loading? For example, if we have a circuit like this, and if this is the load, if you remember, this was the output impedance. Okay. Somewhere we have said to minimize the loading effect, do you remember the loading effect? We should have ZO way too less than RL. Remember this?
Yes, sir.
Yes.
So we have a very good circuit which has got very low output impedance. All right. So what can you say? Where to use this particular circuit? In case of say audio amplifier, voltage gain. So we will have a cascade of amplifiers. Okay. We'll have a cascade of amplifiers. This output will be connected to, so this is a common emitter stage connected to the common collector stage, and then we will have the load connected like this. So overall, this is your complete amplifier circuit, cascade of two amplifiers. So the effective output will be this, isn't it? And since common collector has got very low output impedance, loading effect can be minimal. So where to use common collector circuit? Generally
For current amplification.
at the output stage or the output side of the amplifier. This will give you voltage gain. This doesn't give you voltage gain, but this gives you current gain, or in other words, it gives you very low output impedance.
सर मीन्स अगर एक कैस्केडिंग कनेक्शन है सर तो उसमें ही यूज कर सकते हैं क्या सिर्फ कॉमन कलेक्टर को सर अलग
This
से
is
नहीं
one
कर
of this is
सकते
one
क्या
of the uses. This is one of the uses, but
ओके सर
there is one more interesting thing about common collector, that is it has got a very high input impedance. So this is also not, again, if Zi is high, we know that output resistance, output impedance of CE is not very large, very small. It is a significant value. But then Zi is very large. So this stage is not going to load the previous stage because Zi is larger.
Large.
So this part basically is called as a buffer. This amplifier is called as a buffer amplifier. All right. So you will find common collector circuits to be useful as buffer amplifiers.
Sir, what is the meaning of buffer?
Buffer का मतलब क्या होता है?
So to
It is something. Yeah, it is something. It is something which is an interface or is an intermediate interface, so that there is no problem. Say for example, if you have this process here, some physical process here, okay, and there is some another thing over here, okay, I need to have an interface between these two, okay, but this should not affect the performance of this guy.
okay, sir.
So इसके लिए क्या होता है कि we have something called as a buffer. All right, is that clear?
Yes, sir.
So that is the reason why it is called, it is also called as a buffer amplifier. All right, so now we move on to the last configuration, the last amplifier, that is the common base amplifier. Common base voltage amplifier. Don't worry, we will have a summary of all the amplifiers later on, so that we can see the effect over there, overall effect. Okay, let us first of all see the circuit diagram. This is your VCC. This is RC. We also have RE. Then we have the biasing resistors. Don't forget that we have to use the coupling capacitor. Now, a common base amplifier, where should we have where should we give the input and where do we expect the output to be? Input will be
between base and emitter.
at emitter,
Base and emitter.
and output will be at collector.
Collector.
Okay, so we have to have another coupling capacitor here where we will provide the input. So this is again your RS, this is your VS, and this is where you're going to connect the load. This is where you're going to get the output. This is going to be your input. How do we make the base common? This is R1, this is R2. How do we make the base common? Yes, this is going to be interesting. You're going to tell me why now this will be your common base circuit. Anyone?
By grounding.
Excellent. What we are doing is we are having the base which is at the AC ground. Base is at the AC ground. Okay, and that is the reason why this becomes a common base amplifier. So this will be C2, this will be C3. Okay, let us look at the waveforms, the input and the output. Oh God, what is this? Okay. So if this is your input, the output happens to be like this. So immediately, what is your conclusion by looking at this figure itself? This is your input. This is your output. So what conclusion can you draw by simply looking at the input and the output waveforms? Yes.
Amplification.
Yes.
Sir,
Number one, we have amplification. Voltage amplification is there. But one more additional thing. One more thing. Common emitter में भी था ना voltage amplification.
Sir, but
It is
उसमें
different.
phase 180
Yes,
degree
there is
shift.
no phase difference between input and
Yes.
output. So we have phase shift
Yes.
between input and output. Just hold on for some time. I'm having some other problem here. All right. Are you able to hear me?
Yes,
Yes,
sir.
sir.
Okay, okay. Okay, now let us see the AC equivalent circuit. So just like the previous circuits, we are going to have an AC equivalent circuit. So we start like this. Oh God, something is wrong here. Okay, hopefully there won't be any more interruptions. All right, so we'll continue with this. This is going to be your RC. This is going to be your load. This is where output voltage will be generated. Source resistance and source voltage. Here I'll be having RE. This is where we get VI. IE, IC. Okay, is something missing here? Guys,
Sir, R1 and R2.
missing. They are missing, no?
Yes, sir.
Yes, sir.
You are going to tell me why. This is correct. You are going to tell me why it is missing. If you have understood the concept of AC ground, you will be able to tell me this answer. See what we have done. This point
Sir, because um
is at AC ground because of this
yes,
capacitor,
sir.
right? So look at what is one end of the R1 connected to VCC, which is
VCC, AC
essentially
ground.
AC ground for us. So
Yes,
Yes,
sir.
sir.
grounds on both the sides of R1. So it is shorted out,
And and
isn't
R2
it?
also the same
There
thing.
is,
Yes,
yeah,
sir.
simply R2 also have the same problem, the same issue, the
Yes,
same concept, right?
Yes, sir.
So we don't have R1, R2 here. All right. Now let us have a look at the H parameter equivalent circuit. Everyone clear with the AC equivalent circuit?
Yes, sir.
Okay.
yes, sir.
Yes, sir.
Let me draw the H parameter equivalent circuit now. Okay, as per our convention, we will first draw the H parameter equivalent of the device. Okay. Please remember, these are standard equivalents. So be careful about the current generator direction, that is the current source direction. Now you're going to tell me these parameters. This will be the base, this is the emitter, and this is the collector terminal. So what should be this parameter? This one, H
HIB.
H I
B.
B. What should be this? H
Sir,
HB.
HRB
R B
into VO.
into VO. Excellent. What should be this? This one,
Sir,
current generator.
HFB.
HFC. Sorry, HFB
HFB.
into IB.
I.
What about this? 1 by H.
HO.
Is that right?
सर जो करंट सोर्स है सर HFB into IE होगा ना.
Sorry, I. Sorry. एक minute. Correct. Nice observation. So this should be I. ठीक है?
Yes, sir.
All right. Now we have a simpler figure here. Just to complete the other part of the circuit. This will be your RE. This will be RC. You have the output voltage generated. RL. This is going to be the collector current. This is going to be the emitter current. This is going to be the source current. This is where I get VI. This is where I get VO. Okay, looking from here, what do I have? The device input impedance,
Device input impedance,
the device output impedance. From here,
Circuit
input
input.
impedance,
circuit input impedance.
circuit output impedance. Okay, so let us start with the input impedance. A, input impedance. Okay, what is the value of HRB from the table? Can anyone find out? We already had the table, no? In one of the
It
lectures.
is 2.9 into 10 to the power minus 4.
So yes, so generally or typically HRB is equal to 2 point, repeat, 2.5,
9 into 10 to the power
2.9.
minus 4. Yes, sir.
Okay, into 10 to the power
Minus 4.
minus 4. Okay, so nearly. So what about this? This is very, very small, isn't it? This value is very small. So nearly 2.5. Okay. So this value is very small. So again, HRB into VO is going to be a very small quantity. Agreed?
Yes,
Yes.
sir.
So
So we can say that a very small part of output appears at the input in this case. Very small part of the output VO appears at the input. So I can neglect this term or ignore this term. So ignoring that, my device input impedance ZE happens to be simply HIB. Okay, neglecting HRB into VO. Why? Because HRB into VO happens to be a very small quantity. So I can ignore the effect of this HRB into VO, and my device input impedance now is simply HIB. What about the circuit input impedance? Have a look here.
ZE in
This
parallel with
So
RE.
it is ZE parallel.
parallel to RE.
RE.
So that is it. So that is ZE parallel to RE. This is the first thing that we get here. All right. Next, the output impedance.
That is RE.
Yeah. All right. Okay. Next is output impedance. So looking from the output side, the device side, what is the very first thing that you see here? 1 by HOB. What is the value of HOB? What is the typical value of HOB? Go back and see.
0.49 microsiemens.
So HOB typically is 0.49 microsiemens.
Microsiemens.
1 by HOB will be what? Is what? Call this nearly equal to 0.5 for the time being. So 1 by HOV is what? 2 mega
2
ohms.
ohm, 2 ohm, mega ohm.
Don't forget this micro, okay, which is a large quantity.
Yes, sir.
Okay, so a very large resistance is seen. If you look into the circuit, into these terminals, a very large resistance is seen, which is equal to about 2 mega ohms, which is a large quantity. Okay,
Yes, sir.
that is one first observation over here. Again, since output circuit has little effect upon the input, that is output voltage has little effect upon the input corresponding to this particular value that we have seen, what we can say is that the output impedance ZC is equal to 1 by HOP, a very large value. So this large value is going to overpower anything else that is there. Okay, and so we can say that the the device output impedance ZC is 1 by HOB.
By
Right?
HCP.
So remember that the output impedance of common base, the transistor in common base configuration is a very large quantity. Uh, this will also be seen if you look at the characteristics, output characteristics of common base circuit. All right. In fact, you have found those out. Correspondingly,
Yes,
the
sir.
output impedance of the circuit now is what?
ZC in parallel with RC and in
Excellent.
parallel with RL.
ZC in parallel with RC.
RL.
RC in parallel with RL.
RL कति किधर आया बीच में? It
Sir,
is
RC is parallel to ZC.
yes. Remember RL नहीं आएगा picture में because we are looking into this circuit, no? As if this RL is not there. So looking into the circuit, we see only RC parallel ZC. All right. So this is our equation for output impedance of the circuit. Next is the voltage gain. Again, voltage gain equation happens to be AV, which is VO by VI. How is VO generated? When collector current flows into a parallel combination of RC and RL. How is VI generated? It is simply IE into HIB. You're getting this?
Yes, sir.
Yes, sir.
So the ratio that I get for voltage gain is IC RC parallel RL divided by IE into HIB. Okay, or I can simply write this. What is the ratio IC by IE? In case of common base, it is HFB. See here, this IC is generated. This IC is generated because of HFB into IE. All right. So I can write here as
Yes, sir.
HFB into RC parallel RL divided by HIB. And we see that there is nowhere any negative sign involved. This is one more confirmation that the output voltage is in phase with the input voltage. And of course, we do get significant voltage gain, just like common emitter. All right.
Yes,
Next, we
sir.
Yes,
see
sir.
current gain. So device current gain is what? HFB. This is the current gain, IC over IE. That is your device current gain. So what is the circuit current gain? Again, follow the same procedure just like what we did for common emitter using current divider equation on both the sides. Then you will get HFB into RE divided by RE plus ZE into RC plus RL. This you have to, for common collector and common base, the current gains you have to work out in a similar way like common emitter. Like this I would want you to derive on your own. That will be a practice. Power gain. Device power gain is AV into HFB, and circuit power gain AP is simply AV into AI. So that is how we get the circuit power gain. All right. Is this okay?
Yes, sir.
All right. So we have seen the derivation for common emitter, common base, common collector, voltage amplifiers. I think we've already run out of time. So next time we will just have a comparison of tomorrow. That is, we'll have a comparison of these voltage amplifiers. What are the typical values, and where is the possible usage of such amplifiers? After that, there is now what we have done is what is called as the approximate analysis. What we have done is till now is the approximate analysis. In one of the lectures, maybe tomorrow itself, we will go for what is the accurate analysis, which is a little bit lengthy, but don't worry, it's just the way in which it is derived. So you can analyze the circuits. So you can analyze the circuits using either approximate analysis or a more accurate analysis. We'll see this accurate analysis tomorrow. ठीक है ना?
Yes,
Then
sir.
we will conclude the unit by seeing what is called as the AC load line now. Okay. Somebody had asked me a question about AC load line some days back. So that is there in the syllabus now. Obviously, without AC load line, we can't do anything related to amplifier. So I will actually take an example and work it out as far as AC load line is concerned. Okay. Any doubts, any questions so far?
No, sir.
No, sir.
Very few people are attentive. That is what I have observed.
No, sir.
But this is going to be a problem for them. I'm repeating again and again. All right. Very few people are attentive. This is a warning sign. I'm again giving you these warning signs. Anyways, so we will stop here for today. Thank you.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.